Welcome to this presentation on solving unique length 3 palindromic subsequences problem. In this session, we will dive into the problem, explore an effective approach, and review the solution in C++. The task at hand is to find the number of unique palindrome subsequences of length 3 in a given string. A palindromic subsequence is a sequence that reads the same backward and forward. For example, ABA and CCC are palindromic subsequences while ABC is not. In our example, even the string AABCA, we can identify three unique palindromic subsequences ABA, AAA, and ACA. Conversely, the string ADC does not contain any valid palindromic subsequences, yielding an output of 0. To understand this problem better, we need to clarify what a subsequence is. A subsequence is simply a sequence derived by deleting some or no characters from the string, while maintaining the order of the remaining characters. Now, for a subsequence to be palindromic, it must read the same forwards and backwards. This is crucial as we are interested in length 3 palindromic subsequences. A classic example of such a subsequence is ABA, where the first and last characters are the same and the middle character is different. Let's now discuss how we approach solving this problem. Our goal is to count distinct palindromic subsequences of length 3. The subsequence must be in the form ABA, where the first and last characters are the same and the middle character is different. The plan is as follows. Step 1. Identify the first and last occurrences of each character in the string, and then for each character, check if the first and last occurrences are distinct. If they are, count the distinct characters between these occurrences which form valid palindromic subsequences. Let's break it down further. We begin by iterating through the string and storing the first and last positions of each character. This will help us track the boundaries of potential subsequences. For each character in the string, we check if its first and last occurrences are distinct. If they are, we count the distinct characters between these positions. These characters will form unique palindromic subsequences. Now let's dive into the code. Here is the first part of the C++ solution. We declare two vectors to store the first and last occurrences of each character. Then we loop through the string to fill these vectors accordingly. By doing this, we ensure that we know the positions of the first and last appearances of each character. Continuing with the solution, we loop through each character from small a to z. For each character, if the first occurrence is distinct from the last, we check the substring between these two positions. We then count the unique characters in that range, which contributes to the total count of valid palindromic subsequences. The result is stored in the variable ans, which is returned at the end. Let's now look at the time and space complexity of our solution. The solution has a linear time complexity of big O of n, where n is the length of the string. This is because we perform a linear scan of the string to find first and last occurrences, and then another linear pass to count the distinct characters in the substring. Since we only need to store the first and last occurrences for each of the 26 lowercase letters, the space complexity is big O of 1, a constant space. Before concluding, it's important to consider some edge cases. If the string has fewer than 3 characters, no valid palindromic subsequence of length 3 can exist and the output should be 0. If no valid palindromic subsequences are found, the output will also be 0. For example, the string ADC does not contain any subsequences of the form ABA. In summary, we have learned how to count the number of unique palindromic subsequences of length 3 in a string. We focus on subsequences that are in the form ABA, and the solution is efficient with a time complexity of big O of n and space complexity of big O of 1. By leveraging the first and last occurrences of each character, we are able to count valid subsequences effectively.